This is an investigation of the force between electric charges. Electrical forces are of enormous importance in nature. On the atomic scale, they far outweigh any gravitational forces. Electric forces hold atoms together and make steel wires strong. They also hold atoms apart and make, for example, water difficult to compress. I have here a tube which I'm filling quite full of water, and a piston which fits and will fall, just fits. It will fall slowly like that. It just fits. Now put this down on a squashy rubber sponge, let go, and give it a sharp crack with a mallet. Water is practically incompressible. In fact, electric forces hold the parts of atoms together, electrons and nuclei. If you want to understand atomic physics and really make much of the models of atomic structure that we use, you've got to know the law of force between electric charges. Scientists enjoy finding a law of force, not just for information, but because it adds to their general sense of understanding nature. It appeals to their sense of simplicity and reduces one more mystery to some form of law and order. We are going to investigate a universal law of force between electric charges. At small distances, electric forces compete well with gravity. Turn on my charging arrangement, please. Give a charge to the balloon. Collect a like charge on my balloon. They repel. At closer approach, more. Bigger force. Now, farther away, less force. Still farther, very little force. Now give an opposite charge, and I get attraction. What is the exact relationship between force and distance? You probably know already. Coulomb's law says force varies inversely as the square of the distance between the charges. That means that at twice the distance apart, the forces are a quarter as big, and at 10 times the distance, they drop to 100th. An inverse square law applies in many cases. For example, the illumination due to a small lamp, when light spreads out in straight lines through clear air, not in fog or muddy water that absorbs the light. Here are 3 books at so much, twice the distance, 3 times the distance from a small lamp. The inverse square law is characteristic of anything that spreads out in straight lines without getting lost. I think I can illustrate that with a fable. Suppose a restaurant has the problem of buttering toast and wants to be very modern and do it with a machine. So the proprietor invents a butter gun with melted butter in here, which can be squirted out in straight line spray of butter like that. Here's the piece of toast, and lines of butter go out and hit it there, and there, and there, and there, and butter it all over. Now, instead of that, lines might go on, and you could put the toast further back at twice the distance, 2 pieces of toast wide, 2 toasts high, and altogether you would put 4 pieces of toast there to intercept the butter, and you'd be half as thick, no, quarter as thick buttering. Inverse square law. At 3 times the distance, 3 pieces of toast, 3 pieces of toast, altogether 9 pieces of toast, and you would get 1/9 of the buttering, economy treatment. A century after Newton guessed at an inverse square law for universal gravitation, Coulomb guessed at a similar law for electric forces. He tested his guess with a torsion balance, rather like the Cavendish apparatus used for gravitational inverse square law test. Here it is: fiber, twisting beam, two balls to carry the charges. In our experiment, we shall use a spring balance to measure the force, like that. Two metal balls that we can charge up, a beam carrying one, and a spring to balance the force between the balls. And over here, a pointer which will show the stretch of the spring on this scale, and that gives us an estimate of the force. I'm going to ask my assistant to take the upper ball away, and we can see if the zero is correct. I should like you to see how sensitive this is. I have here a box of weights, 1 gram, that's too big, 1/10 of a gram. I'm going to ask you to put on 1/10 of a gram on the ball, please, and we'll see what that does to the scale. Now first, let's settle the zero. First, just wait while I settle the zero. I'm tapping the balance to free the bearings. Starts with a zero. There, about there. Now put on 1/10 of the gram. Load it up. 1/10 of a gram is within 2%, 1,000th of a Newton. And you see it's going to settle down very close here to 10. And so each of these scale divisions represents 1/10,000th, roughly, of a Newton force. Take the load off, please. Now I shall show you how we measure the distance apart of the two balls. We move them till they're 1 span apart, or 2 spans apart, like that. I'm going to call each of these distances a span, though in fact you'll see that they are pretty well 15 centimeters each. 15, 30, 45, but we shall not use those numbers in our experiment. I shall just call them 1 span, 2 spans, 3 spans. Here is a record. We shall have distance apart and force, and we shall run from 1 span to 2 to 3. We shall start with one ball far away at infinity, and like this. And then at infinity the force is going to be 0 because we'll start the pointer there. Then we shall start 1 span. First I must charge up both balls. I'm not going to explain this ancient device for charging, except just to say that it operates by induced charges on the plate that I'm carrying. I think that will be perhaps a little more sufficiently charged. Now, please set the balls 1 span apart while I look at the scale. There we are. Force is at 1 span, please record it, between 23 and 25. It's just about 20. Settle down, it'll be 23.7. Now 2 spans, please. Oh, force is much less. Well, what did you expect with an inverse square law? Go further up. Encourage the pointer to stop moving. Then we have 5, 6, 4.8, 5, between 4.8 and 4.0, about 4.4, please. 5.4, sorry. Thank you. Now move to 3 spans. Still smaller force. 3, 2, 2.903, about 2.5. 2.5. Now let's see what that record tells us. When I go from 1 to 2 to 3, an inverse square law makes the forces go down from so much to a quarter to a ninth. And we can test for that by multiplying them by 1 and 4 and 9 to see if we get constant numbers. 23.7, we'll call 23.7, 24 will be near enough. 4 4s are 16, 4 5s are 20, 21.6, say 22. And 9 5s are 45, 9 2s are 18, and 22.5, 22.5. So that I get very closely the same number. Actually, I expect less, because charges leak away along imperfect insulators. And the third measurement is too small to be reliable anyway. The inverse square law is a great general law of force. And to be sure of it, you would have to take a whole variety of experiments over a wider range of distances, with attraction as well as repulsion, with different apparatus, and with different charges. You would find no exceptions other than those due to difficulties of apparatus or leakage and things like that. And then you could trust the law for ordinary sizes of apparatus. And you might let the atomic scientists extrapolate it down to atomic sizes. That's a risk we always have to take in atomic and nuclear science. We assume that the large-scale laws apply, and we test them if we can. Actually, we can test the inverse square law inside an atom, and we find that it does hold there. And now, what happens if we change the charges? I'm going to use a trick to change the charge on one ball. I'm going to bring in an extra ball of equal size, uncharged, touch one ball with that, then when they're together they make one conductor, and symmetry tells me the charge will be shared 50-50 between them. Take away the extra ball and give its charge to ground, then here I shall have one ball with half the original charge. Now let's try that. Here is a spare ball of the same size that I can share charge with that ball with by touching. First of all, let me just look at my zero. See how that looks. Not quite. There. Now, let's charge up both balls, please. Set them one span apart, please. Nearly there. Now this measurement you're going to have to remember. I shan't write it down, just remember what it is. It's just above 18, between 18 and 19, just above 18. Now, swing out the ball, please, and we'll share 50-50, and give my share to ground. Now, find out what it is now. Little down, little up. Whoa. And it's not far from 9. It's between 8 and 9. Half 18 would be just 9. And it's a little less than half, but it's not far from it. Swing out the other ball, please, and share 50-50. Bring it in. One span, please. Actually, I don't need to do this second test. I appeal to symmetry. We already know the force is proportional to one charge, so it must be proportional to the other charge. After all, how do the balls know which is agent and which is victim? But in fact, I see the force is just about 4, just about halved. So we can say that the force is proportional to each of the charges. So now we can return to our original statement. Force is proportional to number of elementary electric charges in excess times number of elementary electric charges in excess over distance squared. Some of you may think that we have proved Coulomb's law, and others may say this is just a poor, rough test. But the wise scientist develops a taste for good form in laws and can often jump to the right law on poor evidence. Such rash, clear-sighted guessing is good science, if the result is then tested. So I ask you to accept the inverse square law for the moment and watch while we make a magnificent sensitive test based on good theory. Good theory is not just wild imagining, but argues with sober, hard-headed reasoning like this. If, then. If, thus, then. I shall argue, if Coulomb's law holds, then if we have a large hollow metal ball with an electric charge, we find no electric effect inside. And the converse holds. If there is no electric effect inside a hollow charged ball, there must be an inverse square law of force between charges. Here's the argument. We have a large, round, conducting ball, give it charges, say plus all over like this, and then look for electric effects. Outside, we shall certainly find some effects. Would you like to see the ball? A large copper ball, hollow, so that we can investigate inside. Charge it up, please. Take a sample from outside on a metal ball on an insulating rod. Bring it across to my electroscope. There's plenty there. Now let's get back to the argument. Suppose we put two small metal balls touching each other very close to the big ball. Then these make all one conductor, and this big positive charge pulls negative electrons this way, so that we shall get negative charges all over there and positives left here. Then if we separate these two and carry each in turn over to an electroscope, we shall find charge and charge. So much for outside. Now let's look inside. Suppose we put just here a demon observer carrying a test positive charge there. He looks up here at a patch of the copper ball, like that, carrying positive charge all over it. Then this charge will repel his test charge like that. Let's draw a cone of lines down through the edges of the patch. There, like that. There. Then, as well as looking up to a repulsive patch there, he looks down to a counter cone here, to a counter cone, to a counter patch down there. And that patch of positive charge will push up this way. How will those two pushes compare on his specimen plus charge there? Look at the distances. So much, and so much again. This patch is twice as far away from him as that patch. So this cone has spread out to twice as wide and twice as broad there, 4 times the area of that patch. We shall assume that charge spreads uniformly all over the sphere. So there's 4 times the charge there that we have down there. On that score, the repulsion is 4 times as great due to this as due to that. Now remember the inverse square law. If that holds, this is at double the distance of that, and so we shall have 1/4 of the effect at double distance. 4 times 1/4 is 1, so that this repulsion will be exactly the same as that repulsion, and the two of them will exactly cancel out like that. You see, on the score of area and charge, we've got 4 times as much there. On the score of distance, the effect is only 1/4. Now we can install another patch next door and put another cone here, and another patch, and cone, and counter cone, patch, and counter patch. Oh, I know these are getting oblique, but the tangents at the end of a chord make the same angle at both ends with a sphere, and so the obliquity factor is the same at both ends. And so we can put patch and patch and patch and patch and fill the whole sphere with cones, each of them making a pair of forces that cancel out. In that way, we shall get inside 0 total force on a test charge, 0 effect if we put 2 little balls together and then separate them and take them out to our electroscope. So if the inverse square law holds, we expect no effect inside a sphere. The converse is true. If there's no effect inside a sphere, then the geometry of the areas and charges still holds, but if there isn't an inverse square law, just to undo the area factor, we shan't get 0 inside. So this gives us a very critical test. Now let's try it. First, we'll try it outside. 2 balls touch together near the sphere, separate, and take first one, the electroscope, and then the other. Notice the other brings the opposite charge, drives the electroscope lead down. We should expect very little left. Discharge both those. Just make sure the electroscope starts at 0. Now we'll investigate inside. We go carefully into the sphere, and inside, touch the 2 balls together, bring them out, separated. Try this one. Nothing. Nothing. That's our test of the inverse square law. If you want to see a more gross test, let's just take a big charge from outside, plenty, as before, and then go fishing for a charge from the inside. Listen. That assures us of an inverse square law. It's a very good test because it asks for an answer 0, what we call a null result, and it only needs very sensitive apparatus. It has been tried to an accuracy of 1 in a billion. No electric force inside a hollow charged sphere. Complete shielding. And now let us test our test by taking away half the geometry. We can do that by taking away half the ball. Then we shall only have half of each pair of cones, and we shall expect something inside. Now charge it up again, please. Take a sample from outside to the electroscope. There's plenty there. Discharge the electroscope. Necessary, discharge the ball. Take a sample from just inside. You won't go too far down, because we should expect less further down. And we do get something. Take another trip, just inside. We get some more. So you see, this test of the inverse square law does need a completely closed sphere, or at least one with only a small hole. The argument extends further. The result we got for a hollow sphere applies to any closed metal box. It must be closed, and it must be a conductor. The geometry for other shapes goes beyond this course. The charges do not spread evenly all over the surface, but concentrate along edges and corners in such a way that they produce exactly zero force everywhere inside. A small hole doesn't matter. Our sphere had an open mouth, and we can even use chicken netting. Remember, this only applies if the inverse square law holds. But the inverse square law is true, so any metal box and even a wire cage will give complete shielding. Come and see that tried. I have here a large metal table on insulating feet, and I'm going to ask my junior assistant to stand on the table. Comb your hair, please. And then we're going to charge up table and assistant and cage and everything. This wooden rod is a poor conductor. Start up my charging machine. When I connect to ground, all the charges run away through the spark. The leaves fall, the hair falls. This time, nothing happens in the cage whether I connect to ground or not. Hold the rod to me. Take away the charge slowly. Now step off. Thank you very much. A good scientist likes to keep a flexible mind and turn his knowledge to different uses. With your present knowledge, try to answer this problem. What would gravity be like inside a hollow earth? You may imagine it to be made of thin shells like the layers of an onion with a hollow inside. What would you find inside? I'm not going to answer that, but you can with the same argument. Look back on the way we developed this knowledge of law. We started with rough experiments and made a guess with the gravity law as a model. And then we tested our guess and found it probably true in one example. So we stated it as a rule for distances and for the sizes of charge. Already you can use the rule to compare the sizes of charge. Put each charge in turn at the same distance from some standard charge and compare the forces they exert. Then we assumed our rule is true and devised a sensitive overall test. No force, no effect inside a hollow charged metal ball. That gave us such assurance that we call our rule a law, and we trust it far and wide, from thunderclouds to atomic nuclei, and we shall continue to trust it until we find an exception that makes us modify it. Here, in Coulomb's law, we have a summary of nature's behavior. It is part of our scheme for understanding electricity, not by knowing what it is, but by codifying what it does.